Hi, in this video, we're going to talk about IPv4 subnetting and give just a simple example. Okay, so here we have ARIN, American Registry for Internet Numbers. This is the regional internet registry for North America. They assign IPv4 and IPv6 address space to internet service providers. So let's say ISPA has received the 10.0.0.0/8 network from ARIN. Of course, this is a private address I'm using here, and it would be really a public address they would receive from ARIN. Okay, ISPA has that's a /8 network address. So what this gives ISPA is over 16 million total addresses. This allows the ISP to allocate these blocks of network addresses from this address space to its customers. Okay, so remember, subnetting IPv4. Okay, we have a network portion and a host portion. Remember the owner of the address, the network address, cannot do anything to the network portion. That belongs to somebody else. They can only modify the host portion in IPv4 to create their subnets. Okay, so ISPA cannot modify that network portion, those first 8 bits. Okay, that was allocated from the RIR, from ARIN. Okay, they can only modify the host portion, that last 24 bits. So in order to create subnets, the ISP can divide its one large network into smaller networks by using bits from the host portion. Okay, so ISPA is going to actually borrow 8 bits from the host portion, from the leftmost host portion, by extending the network portion of that will extend our network portion of our address 8 bits. So we'll go from 8 bits in the network to 16 bits. Okay, so this modifies the mask for these subnetworks. It will go from a /8 to a /16, 255.0.0.0 to 255.255.0.0. Okay, so ISPA has control of these 8 subnet bits, okay, and can use them to create the subnets. Let's take a look, right? So ISPA can now use that second octet there, the next 8 bits, which is now part of the overall network because it extended its mask, right, from /8 to /16. So now our network address now includes those second 8 bits. So looking at it in decimal, we have the 10.0.0.0 network /16. We have the 10.1.0.0 network address /16, 10.2.0.0 /16, etc. And it's important to recognize it's that subnet mask /16 that tells us that the first 16 bits, the first 2 octets, belong to the network portion. So we can keep on going all the way, okay, keep on going all the way to 255. This actually gives us a total of 256 subnets, including subnet 0, all the way to 255. We can also look at this in binary, okay? So look at the subnet address. We're going from all zeros in the subnet portion and just incrementing it by 1 bit all the way down to all ones in the subnet portion. That's where we get our 0 to 255. Okay, so looking at this another way, we went from ISPA, went from one network of over 16 million hosts, and I put -2 because you can't assign the host address, you can't assign the network address and the broadcast address to an end device. So I put the -2 there. Okay, so we went from one network of 16 million plus host addresses to 256 subnets. Remember, 0 to 255. Each one, little cut off there, 65,536 host addresses minus 2 per subnet. Okay, so ISP-A has segmented its 10.0.0.0/8 network address into 256 subnets. Okay. Each one was 65,536 hosts per subnet. Okay. And now it can allocate those subnets to different customers. Okay, let's take a look at one of our customers. Okay, let's take a look at the 10.4.0.0/16. So if I back up here, we see customer E there in the purple circle. Okay, let's take a look at what their network looks like. Okay, so first of all, it's important to recognize that ISP-A is going to forward all packets with the IPv4 destination address having 10.4, the first 16 bits matching 10.4, whatever, in the destination IPv4 address. It's going to forward all those packets to router R1. That's even in its routing table. So this now has been allocated to you. Okay, customer E has the 10.4.0.0/16 subnet. Okay, we can look at one of the devices on that subnet. Notice that on this subnet, so to customer E, it's just their network, right? They're one network. One of the devices, they has 10.4.16.100/16 is this device's address. Okay, with the subnet mask /16 or 255.255.0.0. Notice that the default gateway address on A is that of the router R1. And you'll notice that all the devices on this network all have the same /16 subnet mask. Okay, and they all belong to the same network, 10.4. They all have 10.4 in the network portion of their address. And they're all using the same default gateway address, router R1. Okay, if we look at this in binary, remember we did this when we looked at IPv4 addressing in a previous video. So here's the host address for A in binary, 10.4.16.66 with the mask 255.255.0.0. We did the AND operation, and it tells it what network it belongs to. Okay, remember, we just copy the network portion in the AND operation. That's just copied. The network address is all zeros in the host portion. Okay, if we look at all the addresses on this network, the first host will have all zeros and a 1, or can have all zeros and a 1. The last host, all 1s and a 0. And the broadcast address is all 1s. So looking at it in decimal, there's our network address, 10.4.0.0/16. There's the address of our first host, which actually has been allocated to our router and is used as the default gateway on this network. There's the last host address and the broadcast address. Okay, we notice that we have 16 host bits. Well, 2 to the 16th minus 2, because we can't use the network address, can't use the broadcast address, gives us 65,534 usable hosts. Okay. All right, we're going to be seeing much more of this in later videos, and this will make more and more sense to you. It's really this simple. Subnetting is really this simple. Okay, it's a little bit more challenging when we are not subnetting on what we call a natural octet boundary, not a /8/16/24. Okay, but this was just a simple example, and we'll get into more examples in the following videos.